We're going to introduce a chapter on reaction equilibrium, and this will be a little different than some of the other chapters we've talked about, but at the same time it requires a lot of what you've learned already. So our goals will be to understand what equilibrium is, to write equilibrium constant expressions, to solve and interpret them, and then to understand what happens to a system at equilibrium when a stress is applied. And your lab will deal with that concept known as Le Chatelier's principle, and we'll hit your lab at the end of the week. So previously we learned about reactions that occur in one direction. So for example, if you have magnesium and hydrochloric acid, those substances will react to form magnesium chloride and hydrogen gas. And you did a reaction very similar to this single replacement reaction earlier in the year. Instead of magnesium, we use zinc. In AP chemistry, we actually do this reaction and we collect the hydrogen gas in a eudiometer. And that's a very fun lab that we do at the beginning of the year. So this first equation shows just a forward arrow where the reaction is going in the forward direction. And when all of one reactant is used up, is that the limiting or the one in excess? The limiting, because the limiting reactant is used up completely and it determines how much product you generate. So when all of one reactant, the limiting one, is used up, then the reaction is going to stop. So you're only going in the forward direction. For example, hydrochloric acid reacts with water to generate chloride ion and hydronium ion, and you can show this in regard to conductivity because the ions can move freely and they will conduct electricity, which can be measured. This is a precipitation reaction that you ran earlier this year where you have sodium chloride reacting with silver nitrate to generate sodium nitrate, and silver chloride is a white precipitate. So this too, precipitation reactions go to completion, and you ran that earlier in the year, and we'll also be using silver nitrate in the lab to generate a precipitate. Also, when you generate rust, iron 3 oxide is rust, which is generated from iron undergoing oxidation. So each of these reactions only goes in the forward direction, and you of course find that with single replacement reactions as shown here, because those are irreversible reactions. They only go in the forward direction. Now, not all chemical reactions go to completion. Sometimes reactants are left over. Sometimes products react with one another to reform reactants, and this is where you have reversible reactions. Now, rather than writing the reaction multiple times, we simplify it. For example, nitrogen dioxide is a brown gas. When nitrogen dioxide reacts with itself, it forms dinitrogen tetroxide, which is colorless. And you know which gas is being generated based on color. So when it's colorless, you've generated this, and then you'll see it'll turn brown, you've generated this, etc. So rather than writing the reaction forward and writing the reaction in reverse, we simply do this, where you have a reversible reaction. It goes both in the forward and the reverse direction. And we can take a look at this in the following video.
We start this experiment with 3 tubes containing red-brown NO2 and colorless N2O4 in equilibrium. First, one tube is placed in hot water. A second tube is placed in cold ice water. After a few moments, we note that the tube in hot water has darkened in color. It now contains more brown NO2 than the tube which we kept at room temperature. The tube in ice water has less brown NO2 in it. It is much paler because the equilibrium has shifted to favor the formation of colorless N2O4.
And you also can determine if the reaction is endo or exothermic based on the color changes. We'll get to that next time. We'll go back to that video and analyze it. But what's really nice with these equilibrium systems, when you have a color change, you know whether the forward or the reverse reaction is favorable based on the color change. So when you've got brown, the reverse reaction is favored, and when you have colorless, the forward reaction is favored. Reversible reactions. Now don't get upset because you can write those double-headed arrows a lot of different ways, and I'm just going to mention this because when it comes to the remedial quiz, I can't really make those arrows very easily. So in your notes, when I draw them, I tend to do this. I've also seen it written this way, or you can even just do this. And I don't really like this because you see that with resonance structures too, so, but it is what it is.
Which one would you prefer?
What you'll see me doing more often than not is this, although I will warn you in the remedial quiz, I had no choice but to do this. So reversible reaction means the reaction goes both in the forward and the reverse direction. And sometimes you'll see like that. That means the reverse reaction is favored as opposed to this, meaning the forward reaction is favored. When the rates of the forward and the reverse reactions are equal, we say the system is at equilibrium, and we'll get into that, and we've talked about rates already. So these two reactions right here, this reversible reaction, occur at equal rates but in opposite directions. And when the rate of the forward reaction is equal to the rate of the reverse reaction, then we say that we have a state of chemical equilibrium. It is a dynamic process, not static. So once the equilibrium is established, that doesn't mean that things stop. It means it's still going forward, but it's still going in reverse at equal rates. So they're dynamic processes, not static. You can think of this as bees going in and out of a hive. They don't just all go in, sit on the couch, and watch TV, even though that's what you saw in the bee movie. They go in, they come out, they go in, they come out. Think about when you go to a football game or a concert or any type of sporting or event that involves an arena. People are not all sitting in their seats at the same time. Someone's in the bathroom, there are people online for food, drinks, etc. So it's a very dynamic process. Think about our parking lot, especially in the morning, coming in, coming out, very dynamic, not static, okay? What we want to look at first is what happens as the reaction reaches equilibrium. We're going to look at changes in reactant concentration, in product concentration, as we approach equilibrium, where the rate of the forward and the reverse reactions are equal. So shown here is the same reaction we talked about. What do you know about reactant concentration over time? It's going to decrease because reactants get consumed, and product will increase because those concentrations go up. So what you're looking at here for this reaction is concentration on the Y versus time in minutes or sometimes seconds on the X. So reactant, nitrogen dioxide, is being consumed. Its concentration goes down, and then it hits this plateau, which I'll get to in a minute. Dinitrogen tetroxide is being generated, so its concentration is increasing until the plateau. This plateau is the region of equilibrium, and this is the time at which equilibrium is established. I'm not saying that concentrations aren't changing. I'm saying at that point the rate of the forward and reverse reaction are equal.
What causes this reaction? If there's not a second reactant, what makes it go to?
Well, you have two reactants there, even though they're the same. And in kinetics, we didn't get into molecularity, but even though the order with respect to that reactant could be one, you'd have to test for that. The fact that you have multiple of it, they react with each other. I think I have this reaction, but you could imagine if you have nitrogen dioxide, let's say nitrogen's here, oxygen, oxygen, and here's the other one, and they, you know, moving all over the place, and then bam, those nitrogens hook up, and then you've got the oxygens coming out. I think I've got that video though, and I can show it to you. Shown here is the generation of ammonia, NH3, from nitrogen gas and hydrogen gas, and again, even if these weren't labeled, you can identify them. The reactant concentrations will decrease. You can see that with the hydrogen and the nitrogen. Why is the green line above the blue line?
There's small moles of hydrogen gas.
It's a 1 to 3 mole ratio. For every 3 of these, you need 1 of these. Hence, it's higher. And then why is ammonia increasing in concentration over time? Because it is a product. And equilibrium is established here, and you see the plateau where the rate of the forward and reverse reaction rates are equal.
Why isn't the red line above the blue line if it has more, like, molar?
Say it again.
The two for the coefficient of the product, why is the red line lower than the blue line?
The red line is above the blue line at equilibrium because it's a 1 to 2 mole ratio.
But on the other side.
Because initially, how much product do you have? 0. And that's why it starts low. And that's a good question. And a better answer. Reversible reactions are very common. You see this, for example, with recharging of an automobile battery, recharging of our newer type of rechargeable batteries. A battery contains sulfuric acid, and it's got lead and lead 4 oxide, and when those 3 reactants react, they generate lead 2 sulfate, water, and energy. Is this an endo or exothermic reaction? Exo, because energy is on the product side, so is delta H positive or negative? Negative. So the reaction typically runs in the forward direction when you turn your car over. Now, if the battery's dead, you want to jump start it, and so what you have to do when you jump start it is provide a battery, because you've got to provide the energy source. In an endothermic fashion, the lead 2 sulfate will react with water, and you'll generate lead, lead 4 oxide, and sulfuric acid. Why would you flood an engine if you keep trying to turn it over?
Because the water will stop reacting with the sulfur.
Right, you might have had a little bit of water in there, and then you keep trying and trying, and you're basically going to flood that engine. All right? Those examples I gave you. Now, typically what we like to look at is the change in concentration over the change in time for rate. But you can also look at mass, temperature, color, conductivity. There's quite a bit. But for our purposes, we're going to look here. And I don't think I gave you any type of graph like this. This would be really more for advanced chemistry. But what I would expect you to be able to do is if these weren't labeled, how do you know the red line's a product? Because it's being generated. You start with nothing and you generate some. The others are the reactants, and you could tell which was which based on the coefficients and the positioning of the hydrogen gases compared to the nitrogen gas.
In that reaction, would the backward reaction be favored because would it be more thermodynamically favorable?
Which, this one?
Yeah. Like that, wouldn't the entropy get like larger as
That's tricky though, because entropy alone is not the only factor that determines thermodynamic favorability. Generally speaking, synthesis reactions are exothermic, which is better for thermodynamic favorability. So in this reaction here, you have an exothermic reaction that illustrates order. So the question in regard to thermodynamic favorability here, you would have to look at the delta H and the delta S. Now at very low temperatures, you would expect this to be thermodynamically favorable. At very high temperatures, no. But you've also got an equilibrium type of reaction, and if you knew the value of KEQ, which we'll calculate, if it's greater than 1, then that leads to a negative delta G. But that's a little complicated, and I don't think we'll make that link this year. But a good question nonetheless. All right. So when you're at equilibrium, the rate of the forward and reverse reactions are equal. Their rates are equal. So what we want to do is we want to show some type of relationship between concentrations of reactants and products using what's known as an equilibrium constant. Equilibrium constant, K for constant, capital K, which is different from the lowercase k that you saw with your rate laws. So we can establish a relationship between concentration of reactants and products using an equilibrium constant KEQ. And the following reaction would be an equilibrium type. Again, same nomenclature we've talked about for multiple chapters. Capital letters for substances, A and B are reactants, C and D are products, lowercase letters for coefficients. Our equilibrium constant expression is KEQ. K for constant, that's a capital K, EQ for equilibrium. That is equal to the concentration of products raised to their coefficients, and it's the product of those products you're multiplying. Reactant concentrations raised to their coefficients. KEQ expression. Your rules for writing them: the numerator contains the concentration of products, the denominator, reactants. The exponents are the coefficients. So if you wanted to write the equilibrium constant expression for this substance, this equation here, you can see initially these two substances are reacting to form phosphorus pentachloride. As the reaction goes, the rate of the forward reaction will decrease as these are being used up. As this gets generated, it will then break down into these substances. So initially then this will increase until equilibrium is established where the rates of the forward and reverse reactions are equal. Your KEQ expression then is product concentration over reactant concentrations, and you multiply those two. There are some rules for writing KEQ expression. Some of you are really spent. You must have stayed up too late last night. You are exhausted. Try and refocus. It's a very, very easy concept. You won't have any difficulty with it if you can focus. You always put gases in equilibrium constant expressions. You always put aqueous substances in equilibrium constant expressions. You do not put solids, and you do not put liquids. And we'll talk about why in a little more detail in a bit. The value of KEQ remains constant only if the temperature remains constant. If the temperature changes, the value of KEQ changes. Temperature is the only factor that can alter the value of KEQ. Only gases and aqueous substances are in KEQ expressions, not solids or liquids. Their concentrations don't change, so we don't include them. And let's make sure we can write KEQ expressions. I think you'll find this to be relatively straightforward. So for those of you who don't have your notes, you'll want to write down the answers for 1 through 4 here. We'll work through this carefully. In the first one, we've got 2 moles of sulfur dioxide gas reacting with oxygen gas in an equilibrium fashion to generate 2 moles of sulfur trioxide. And what we want to do here is we want to write the KEQ expression. So what we've got here we write KEQ products on top. The product is sulfur trioxide. You put it in the brackets because that represents the concentration of, and you raise it to its coefficient over reactant concentration. That's sulfur dioxide raised to the power of 2. And this is a product, products, not products from the balanced equation, but you're multiplying, so the product of, and you've got oxygen, and that has a coefficient of 1. This is a KEQ expression. And again, don't think you'll have any difficulty there. In the second one, you always write KEQ. What goes on top, product or reactant? Product. So you've got chlorine gas raised to what power?
I can't see the equation.
I know, because you guys don't have your notes, silly gooses. 2 would be correct. What's the other product?
1,
And it's a gas raised to what coefficient?
2,
I'll flip the screen in a sec. What goes on the bottom?
reactants.
So you've got hydrogen chloride gas raised to the 4th because of the coefficient of 4, and oxygen. And it would look as such.
Does that if you write the hydrogen chloride first? Like if you wrote oxygen and then
Doesn't matter, but I usually just do it in the same order. It's easier. All right, for number 3, well, you can, but what don't you include? You don't include the carbon, which is the solid. So the product is carbon monoxide raised to the power of 2, and you just put that over carbon dioxide. You don't include the carbon because it's a solid. It's still part of the balanced equation, but it doesn't, it's not part of the KEQ expression because its concentration doesn't change, so we're not going to include it.
All of these chemical formulas are reversible, so does that mean that the products and reactants can be like on the numerator and denominator like interchangeable?
You still write it the way it shows. The fact that it's reversible says that these two react to form this, but this can break apart or decompose to reform reactants. But when you're writing your KEQ expression, as written in the forward direction, the product will be in the numerator, the reactants will be in the denominator. And then number 4 looks a little bit funky. Again, you include gases and aqueous, not solids and liquids. And I include this expression here because your lab involves a similar balanced equation, and I didn't want it to look foreign to you when you did the lab, so I include it here. So number 4 at the top of the screen then would be KEQ. Product, you've got a hydrated cobalt ion. This is a complex ion. It actually has a pretty funky name. You include the charge of that ion inside the bracket. It didn't have a coefficient. You have chloride ion raised to the power of 4, So you include aqueous substances. Those products are aqueous, which you include. What do you not include in the denominator? Water. How come? Because it's a liquid. So the aqueous substance as such, and these are a little far apart, but just the way I wrote it, not that it's meaningful. So product concentration in the numerator, reactant concentration in the denominator, the coefficients become the exponents. And that's how you write a KEQ expression. Questions there? Well, now that you know how to write them, what do you think we're going to do with them? We're going to solve them. So we're going to solve when given concentrations. We're going to calculate KEQ values, and we will interpret KEQ values. And the other thing we want to be able to do today is we want to also be able to solve for concentration if all the other concentrations as well as the KEQ is provided. Questions on writing the KEQ expression? It looks pretty good. Not worried about it? Good, because it's very, very simple. And now it really just becomes a matter of math and memorizing one concept. Although if you understand the concept, you don't even have to memorize it. And we'll get there in a sec. Okay, so we want to be able to calculate KEQ. It says when the concentrations of reactants and products included in the KEQ expression are known, the value for KEQ can be calculated. Although units of KEQ can be determined, they are dependent on the balanced equation and they can differ for different reactions. So to make things easy, we just don't use units for KEQ. So it's the one time you're going to get away with no unit for KEQ and not lose a point. All right? No unit for KEQ is necessary. So now what we want to do is we want to use these equations to calculate the value of KEQ and the concentrations for substances in the equation will be provided. And this too I think you'll find pretty straightforward, very simple math. In the first example, we have hydrogen gas and iodine gas reacting to form 2 moles of hydrogen iodide gas. The concentration of hydrogen gas, iodine gas, and hydrogen iodide gas are all provided. Your approach to calculating the value of KEQ is to always write the KEQ expression first. So the first thing we want to do is write our KEQ expression. So KEQ is equal to hydrogen iodide squared over hydrogen gas times iodine. And that's why you have to be able to write a KEQ expression. This shows the relationship between products and reactant concentrations. Questions on writing KEQ? Once you write it, then it's pretty easy. You plug in those concentrations and you solve it. Now when you write the KEQ expression, you need concentration brackets because these are concentration brackets as we talked about in the previous chapter. When you go to solve it, you can just use parentheses, concentration of hydrogen iodide, 0.0173 molar, and you have to square that because of the coefficient of 2 from the balanced equation. You've got 9.1 times 10 to the negative 3 molar, 5.9 times 10 to the negative 4 molar. Now with most calculators, the only parentheses that you need are the ones in red. If you have the multi-view, you probably need all of them. Plug it in your calculator now to make sure that you are solving this type of problem correctly. You don't want to lose points for a multiplication error. I got a KEQ value of 56. See if that's what you got.
Now we're gonna have to calculate the mole value, or
For right now, you're calculating KEQ, and we're going to interpret it, and then I'll show you how to calculate the other pieces.
oh, so like for that one, you're just giving us the okay.
So we have to square this one.
All right, but you're plugging it in. You got the correct answer?
At 5.6.
Try again. Make sure you plug in 0.0173 square.
Times
Yeah.
10 to the second.
Yeah. So instead of times 10, remember instead of the times 10, we were hitting the EE or EXP button. That's from the beginning of the year. Chris, who usually, oh, Caroline is out? Is Caroline out?
Yeah.
And Annalise? All right, so you have 56, yes, yes? Okay, question. If KEQ is greater than 1,
Forward direction.
why?
Because the concentration of the product is greater than the concentration of the reactant.
Exactly. So if KEQ is greater than 1, that means the product concentration is greater than the product of the reactant concentrations. So when KEQ is greater than 1, the forward direction will be favored. And we'll look at some others. And that's in your notes. We'll go through that. I just wanted to throw it out there. Do you want to try and give number 2 a try yourself, or you want to do it together? Want to try? Try number 2. It's on the screen. I'll highlight it in green. And see if you can do that one. I'll do it as well, and we'll see if we all have the same answer. And remember, you start by writing the KEQ expression. And again, make sure you're comfortable with your calculator. What'd you get?
No, it's 0.844.
Yes.
346.
Yes.
I mean, no, 350.
That's what I got.
38,442. Yeah.
In your calculator,
Second PRG.
in your calculator, you had 38,411, right? You only want 2 sig figs. So then you replace those back 3 digits with zeros, or you can do scientific notation. Whatever you prefer is fine.
Alright, now I got it.
Are we good? You feel confident? Yes, yes? All right, we're just going to shake it up ever so slightly. I do want to go over the interpretation piece. We'll take a look at that. And then the other thing I want to do is, instead of just solving for KEQ, let's say KEQ is given, ammonia concentration is given, nitrogen concentration is given. Are you able to solve for hydrogen concentration? And again, it's all math. You're very strong at math. You'll be great with this stuff. All right, in regard to in the interpretation, it says if KEQ is greater than 1, then product concentration is greater than reactant concentration. So we know that KEQ is equal to product concentrations over reactant concentrations raised to their appropriate coefficients. So, and this is in your notes, so you can just watch. When KEQ is greater than 1, that means that product concentration is greater than reactant. Well, that means that the forward reaction must be favored because you made more product than you had reactant. If you look at both of the problems we did, KEQ of 38,000, if they ask you which reaction is favored and why, in this case, the forward reaction would be favored because KEQ is greater than 1. In that case, delta G would be negative and you'd have a thermodynamically favorable reaction. How about here? Why is the forward reaction favored here as well? Because KEQ is greater than 1. Okay? So when KEQ is greater than 1, the forward reaction is favored. Now if KEQ is less than 1, not negative, but rather times 10 to a negative exponent, then you'll see that reactant concentration is greater than product concentration because you'd get a fraction less than 1, so between 0 and 1. In this case, the reverse reaction is favored because you have more reactant than you do product. Now, if KEQ is equal to 1, what can you say about product and reactant concentration? They have to be equal because that's the only way you'll get 1. And that is a state of equilibrium. And for the record here, delta G would be 0. And neither problem had a KEQ less than 1. So for example, let's say you had 3.0 times 10 to the negative 3. So you're going to have a negative exponent there when KEQ is less than 1. Now if KEQ is huge, like greater than 10 to the 10th, then the forward reaction solely occurs. It goes to completion. Yeah. Typically greater than 10 to the 10th power.
If it was less than, like if you had 10 to the negative 10th, would that be kind of the same thing, like the decomposition is always favored?
The reverse reaction is always favored, yeah, depending on what type of reaction you have. All right, so you know how to solve KEQ. When KEQ is greater than 1, the forward reaction is favored. When it's less than 1, the reverse reaction is favored. When it is 1, you're at equilibrium. Delta G would be 0. For the record, you don't need to know this at this level, but delta G then here is negative versus positive for the forward and the reverse, but you don't need to know that at this level. All right, the last piece of the puzzle, and then you'll have a lot of time to practice and really get this concept under your belt. The key to being successful from here on in with all the testing you have is use your classwork time wisely. Make sure you understand the lesson fully before the next class. Then you'll be successful. The last piece of the puzzle is to calculate the concentration of a reactant or a product when KEQ is given, as well as the concentrations of all the other substances. So here we're going to be solving for the concentration of one substance. This just requires being meticulous, plugging things in properly, using your calculator properly, and you'll be highly successful. So we're going to walk through probably 2 or 3 examples together, and then I'll let you solve. There's 5 of them here. We'll do as many as we need to do until you understand. We'll get through these, and then you'll have some classwork for more practice. And I would think by the time you leave today, if you really work hard, you'll be pretty confident with this concept that's going to be worth about 70 points of your quiz. All right, on number 1, it says use the equation and information provided to calculate the concentration of the valueless substance. So our approach here is always to write the KEQ expression. So the first thing I'm going to do is write KEQ is equal to hydrogen iodide concentration squared over hydrogen gas times iodine. They're all gases, they're all included. Now I want to solve for this one. If I'm solving for the numerator, I'm going to go ahead and cross multiply. I've got hydrogen iodide concentration squared is equal to KEQ, hydrogen gas, iodine. So far, so good? I don't want hydrogen iodide squared. I only want it to the first power. 2 times what is equal to 1? A half. So I'm going to take the square root of both sides. and you know that the square root is the same thing as the 1/2 power, correct? Yes? I mentioned that here, you'll see why. So I'm going to take the radical of this. Now I'm ready to plug and chug away. I've got hydrogen iodide concentration is equal to KEQ was given as 56. Hydrogen gas at 0.0091 molar. Iodine at 5.9 times 10 to the negative 4 molar. And I'm going to have 56 times 0.0091 times 5.9 EE negative 4. And I'm going to take the square root of that, or you can take it to the 1/2 power. And I've got a concentration of 0.017 molar, unit of molarity for concentration. And you can test that out to make sure it's correct. You can go back and check your work the same way you would do in algebra. It's probably a good idea. And you'd get that KEQ back out. You can do it in scientific notation if you prefer. They're both the same. Don't forget the unit of molarity. So far, so good? Question? Let's try the second one. This will be slightly different. I'm going to show you some tricks. I think if you're just very careful with your math, you'll be okay. On number 2, you've got KEQ, products on top, and they're all gases, so we'll include all the gases, all aqueous. We've got HCl and oxygen. Robin, if you can wait 5 minutes, I would, because it's going to get a little tricky. You can hold on to it so nobody steals it from you. Questions on writing the KEQ expression? You will recall from other types of manipulations we've discussed that you can interchange a numerator on one side of an equation with a denominator on another side of an equation. If you don't feel comfortable with that, you'll cross multiply and then solve for oxygen. But what you will ultimately see, as we have discussed previously, is that you can interchange a numerator on one side of the equation with the denominator on the other side of the equation. So all I've done is interchange KEQ with oxygen. And again, if you don't feel comfortable, you could do this times this times this is equal to this times this, and then divide by those two to get that. So it's all the same. And once you have it set up, then you're just going to plug and solve. So we've got chlorine gas is 1.5 times 10 to the negative 3 molar. That's squared. 0.345 molar squared. 0.555, those are fives, molar to the 4th. And KEQ as such. And just be meticulous in your calculator. Most calculators will only need the parentheses in red. After I do the top, I usually hit equals. And then I'm going to divide. I'm going to open the parentheses. I've got 2.8 times 10 to the negative 4 capital M for molar. And again, go back and plug this in and see if it works. Make sure you're getting the right answer. It's a good check system to use, and I do. Just out of curiosity to make sure you're understanding, KEQ here was 1.0 times 10 to the negative 2. Would the forward or reverse reaction be favored, and why?
Reverse reaction is, or no.
Reverse reaction is correct.
Yeah, because KEQ is 1.0 times 10 to the negative 2, so it's less than 1.
Mm-hmm.
And delta G would be positive.
So do you see the manipulation here? All right. One more together for sure. This one will be a little trickier, and then I'll let you try the others as well as your classwork. Let's take a look at number 3. Number 3 is far more challenging on multiple levels. When looking at the balanced equation, what's the first thing that you notice? You have a liquid in there, and you have aqueous substances which are charged. So do you include the liquid? Do you include aqueous? Yes. All right, so information about the water is given, and it's there solely to confuse you. Don't use the water. It is a liquid.
Does it make any sense to molar water?
Well, it's a liquid, and it's not included in the equilibrium constant expression. So the first thing you're going to do is write the KEQ expression. I'm leaving that on the screen. Write the KEQ expression in your notes or on paper. Let's make sure you've got that cold. Did you get the same KEQ expression that I got? Yes? Yes? We want to solve for this piece. Now that flipperoo thing only works when you've got it in the denominator and you don't. So you want to cross multiply and solve here. You've got KEQ and these complex ions have pretty funky names, so I don't want to confuse you. So when I cross multiply, I have this.
Isn't that cobalt? That needs the cobalt.
This. It's tricky. It's a hydrated cobalt 2 ion. It's very tricky. It's a ligand, and we used to teach it in AP. They took it away. Thank God. All right, I want to solve for this piece, so I'm going to divide by this. And this is what I was trying to get into earlier. This is to the 4th power. 4 times what fraction will get it to the 1st power? 1/4. So I'm going to take this to the 1/4 power to get that to the 1st. Does that make sense?
Can you just do like the fourth root and calculate?
Yeah, same thing. Or you can square root it twice. But if you have something to the 5th power, then you've got to do it to the 1/5 power. So you can do this times this over this, arrow up, 0.25, or arrow up, open parenthesis, 1 divided by 4, close. I'll write it out. All right, let's plug in and solve. Just make sure you put the right concentrations in. So you're going to multiply, divide, and in the calculator, when you do to the 1/4 power, you either do this or this, and some of you have different calculators, so if you're not sure what, we can take a look at it together. You have 2.3 EE3 times 0.4 divided by 0.75, arrow up to the 0.25 power, and the concentration of chloride ion is 5.9 molar, which is pretty high. You also could go back and check that and make sure you get the KEQ out. The other question I have is, with this KEQ, is the forward or reverse reaction favored, and why?
Forward, KQ's greater than 1.
Exactly. Did you get 5.9 molar for chloride ion concentration? Amelia, yes. Garrett, yes. Ethan, yes, yes. It's popping. You just need some practice. Okay, so what we've done today is we've written KEQ expressions. We've solved them. We've interpreted them. And we're now getting somewhat comfortable with calculating concentration based on other concentrations in KEQ. Chemical equilibrium is when the rate of the forward and the reverse reactions are equal. Equilibrium is a dynamic process. It continues to go. It's not static. What we'll get into next time is what happens to a system when you alter equilibrium, when you do something to perturb equilibrium. You want to know how the system responds, and we'll get into that next time. We've got about a half an hour. I'll do 4 and 5 and put these answers on the screen, and you can check your work. I've got to do 4 and 5, I haven't. And I'll give you your classwork that accompanies this chapter. You can do 1 through 8, and it involves writing a lot of equilibrium constant expressions, solving them just as we've done today. And I would think that by the time you work through these problems, you'll have a very high comfort level with this concept. I think if you practice, you'll be very, very successful. Next time, and I don't think our next day together is an FSA day, which will give us a little more time, we'll talk about Le Chatelier's principle. At first glance, it appears to be very tricky, but I have found that the kids have had great success with it, as will you. I'm going to work through 4 and 5 quickly, and I'll put the answers on the screen so they're in the video. Thank you.
Problem on the screen.
Yeah, I'll put your problem on the screen. I'll work it, and you want to get these done. I'm going to ask that you stay at your desk today. If you want to push them together, it's fine. The kids seem to leave a lot of stuff all over the place this morning. Oh, I can't believe I just opened this. Trey, this is yours. I'm sorry. I just like, you know, opening your mail. Oops.
That's a federal offense.
Just grab one. Well, I think it's only a federal offense if it comes in the mail, not if I inadvertently opened up something at school. Hang on, let me do 4 and 5. Do you want to take your quiz? All right, so it's right here. Yes. Yeah, I'll do your quiz grades. I just want to get those 2 problems done and flash them on the screen.
Do you want me to pass out the quizzes?
No, because we still have a lot of non-takers, but I'll give you your grades. First, I have to do numbers 4 and 5. And I'm sorry I didn't break in between, but I just figured I'd let the video run, and then also with your scheduling today, it's just hard. And I think the best way to be successful with this is to manipulate variables, not quantities. Who got the first one? What'd you get?
27 more.
That's what I got. Now I'll do the next one. You don't need one. What do you want in there?
Is he copper?
Yeah, see.
guys want to go?
I'm plugging it in now. I'm trying to write the pieces out so it's easier to follow, just in case somebody needs a little more. What'd you get?
7.2 times 10 to the negative fourth molar.
What'd you get?
7.2 times 10 to the negative fourth molar.
What'd you get? Who else did it? Yeah, I'll mix it up. You're on the movie. Let me see.
You forgot the cube.
No, that's the KQ.
Oh.
Those are interchangeable. That's what I got. So that's my KQ. I'm sorry, that's my chlorine. So if I cube that, and
Yeah, I had a calculator error.
still gonna be in.
0.027. Oh, I have something. 0.027 squared.
I did that.
I might have got
I didn't get that either.
Okay,
Hang
hold
on,
on.
hang on.
Times, parentheses, 2.5 EE,
Something's not right. Let me
negative
see.
4.
0.027 squared times 2.5 negative 4. Do I have all the pieces?
Divided by 1.0 EE, negative 2. Divided by 3.0 EE,
All the right pieces.
negative 3. Raised to the 1 divided by 3. I still got 7.2 times 10 to the negative fourth. What on earth?
How come we didn't
Put
square
O.
this? How come we didn't square that?
Square what?
See how you
Why? How come we didn't square what?
You didn't
Phosphorus
square that.
bromide? I squared it there, I didn't square it here.
to the second.
That's what I did wrong. Let me see if I get it now.
Decimal place. This is 1.
Oh, 2.5.
Ethan, what'd you get?
I didn't do that. I started my class first.
Oh.
Sorry.
Wait, on number 4 for the notes, what'd you get? Like, what was the answer?
0.87 molar.
Alright, thank you.
I think mine's right.
There you go. Yeah, it is.
Mine's right.
You get it right. I got it.
Yes.
Oh, I'm still on the film. How about TV, Dr.
You're a star. This is what I got. So this is my number 4. And this is my number 5. So you can check yours. That's what you got too? Okay, let me cut the video. I just let that run. I wish I